Welcome everybody to today's webinar. My name is Dan Combest, and today I'll be talking about simulating complex boundary motion with generalized internal boundaries. We've had a bit of a break in our webinar schedule, so we're picking up for the rest of the year, and this is the first one. Today, my webinar goals are kind of just introducing ENGYS and some of our CAE innovations, present the overall features and applications of GIB. And we've only got 30 minutes, so really we can't dive too deep into the technical or too deep into each one of the applications. So this is a real top-level perspective of everything. In the end, I hope that you'll obtain a sense of how to create and how to use GIB within Helix. And I'll answer some questions at the very end. If you'd like, you can reply to the meeting invite itself with your question. You can reply to the question dialog within the GoToWebinar application itself. Just a little bit of information about ENGYS. We are global providers of CFD products and services. Originally, we were founded in the United Kingdom in 2009, so we really just finished our 10th year of working. And we've always been focused on enabling open source software within industry. We have deep experience in multiple software libraries, especially foam and open foam, since we have developers within the company that have worked with the open foam code base since before it was even open source, since 1999. We have 7 offices worldwide in the UK, Germany, Italy, here in the US, Australia, South Africa, and Brazil. We also have an established network of distributors around the world in Japan, South Korea, here in the US, France, and Spain. Some of our products that we provide, we have 4 main groups. The first one is Helix, which is a general purpose open source CFD software suite. That's a lot to say, but it is meshing, it is setting up cases, it's post-processing, and that's what I'll be talking about today. Our next product is Elements, which is an advanced open source CFD software for automotive. And I would describe this more of a superset of Helix. So it's everything that's in Helix plus more for things like automation, dealing with external aerodynamics, simulation for automotive, and report generation. So it does a lot more in addition to Helix. Helix add-ons are things that are additional physics or optimization tools. For example, for adjoint optimization, we use this continuous adjoint approach. And so there's a whole set of tools that are built into the Helix adjoint add-on. We also have add-ons for block-coupled solvers, marine hydrodynamics, and also advanced multi-phase flow simulation. And then finally, we have Helix OS, which is an open source GUI for standard open foam that anyone can download off the internet for Linux. And if you'd like more information about each one of these, you can always visit our website at engys.com. Today, I'll talk about the motivation for GIB, a very quick overview of the methodology, talk about moving mesh, talk about Helix GUI and where GIB falls in this sequence of setup whenever we perform a CFD analysis. Then I'll hit a little bit of the applications and leave with take-home messages all within 30 minutes. So first off, dynamic mesh motion. So we have lots of different application areas within computational fluid dynamics analysis that use moving meshes. On the far left, we've got rotating motion, and around this rotating motion, we have a sliding mesh interface. Here in the middle, we have predetermined motion of this vehicle overtaking another vehicle, and this would use some sort of deformation. And if the mesh quality became poor, then there's this remeshing and then mapping of this solution to this new mesh. And then finally on the right, we have this 6 degrees of freedom motion where there's a fluid structure interaction where the fluid is pushing up against this body, and the body has moment of inertia, and it also has these different components that we're able to lump together and try to approximate how a fluid interacts with this floating object. And in this case, there's deformation and smoothing. However, GIB seeks to solve a problem of larger deformations, and maybe larger deformations that wouldn't be captured very easily by the three previous cases that I just presented. So here we've got a life raft dropping off of an oil platform, and you'll notice at the very end, this life raft kind of leaves the domain very peacefully. The origin of Generalized Internal Boundaries, GIB, it really came out of a need to better approximate the optimal surfaces that we calculate inside of continuous adjoint. So if you're not familiar with continuous adjoint, I did a previous webinar on topology optimization that you can find on our blog. And what we're seeing here on the left, we see a three-dimensional perspective, but on the right, we see a two-dimensional perspective of this. And this black line right here, this is actually the GIB interface, and this represents the optimal surface to do something like minimizing pressure drop. So it was originally developed for applications in adjoint optimization. We have this motivation to extend it, and we know in CFD analysis that many applications require large boundary motions and large deformation. I showed examples of all of this. There's several different alternatives. The first would be immersed boundaries, then there's overset grids, there's cut cell methods, and then there's surface motion with remeshing and solution mapping. For immersed boundaries, they're approximate. They maybe lack generality, and overall, it's a poor framework for time-accurate motion representation. 2, 3, and 4 are notoriously computationally intensive, and they're difficult to implement and have additional individual shortcomings of mass loss or continuity errors, things like that. So for GIB, we had this target of having the performance of immersed boundary, but having the accuracy of just a body-fitted methodology that we normally use for mesh motion. Let me talk a little bit about the methodology. Overall, the goals are to implement internal moving boundaries with the same accuracy as a body-fitted mesh. We want to minimize computational overhead and also ensure framework compatibility. What does that mean? It means that it works with every solver, it works with every field operation. Field operation would be something like in situ data calculation. Let me calculate Y plus while I'm running a simulation, or let me calculate vorticity. Or forces, or lift and drag, things like that. We wanted the same input and output interfaces as other boundaries. So we didn't want to necessarily create a new data structure that existing post-processing software might have an issue viewing and maybe have an issue with that users might encounter down the road. We also wanted to be able to apply existing boundary conditions, so fixed value, zero gradient, so Dirichlet, Neumann, Robin boundary conditions on these generalized internal boundaries. So really, GIB, generalized internal boundaries, we wanted it to be generalized. And then finally, we wanted this simple workflow to create and use within an analysis framework. We didn't want something that had, you had to generate a background mesh, like you might do an overset and figure out how these two chimera grids, what was the priority, how do we interpolate between these two, or more than two different grids to create this super mesh. We didn't want to have to do that right off the bat. So the concept behind GIB is that there's this interface snapping, so a projection of an internal face. And so we can see here on the right, we've got this internal face, which is this red line right here. And there's this projection of the internal faces onto a target surface, which is this red line. And there's some local deformation. So here we see this snapping of the background mesh internal faces onto the target surface itself. So there's this actual incorporation into the mesh itself. During this process, there are two new boundaries, one on each side. So one out here and one would be inside of this cylinder. And they're constructed from these internal faces. So if you're familiar with sliding mesh, within Helix or Elements, you'll notice right off the bat that that's a very similar operation of making two patch pairs. All of the quantities needed for the finite volume method are updated locally. So this includes things like volume, weights, areas, etc. The GIB boundary faces give the approximate contributions to the matrix, and GIB can behave like a pass-through surface, so it can be invisible. We can have a normal boundary and have Dirichlet, Neumann, Robin, as I mentioned before. We can also have boundaries with communication, so communicate temperature between two different regions, so we can treat these as two different regions if we like. And any existing boundary condition could be used with GIB because it's so generalized. So far, it's been integrated with all levels of the existing platform. This means within the mesh data structure, the boundary conditions, the finite volume operators, so for both implicit and explicit, also with the matrix solvers, so we're able to reuse a lot of machinery that already exists within Helix by generalizing this new feature. Also field operations, so multiplying, dividing, or adding, subtracting, dot products, cross products, so different operations on these different vectors. It's also fully parallel and has a scalable intersection checking algorithm and also scalable surface-to-surface interpolation. Just one simple verification case. Here we're comparing a body-fitted versus a GIB cylinder. And so these are both static. We're not moving at all. So here we have a body-fitted. This white spot right here is just empty space. And you'll notice right off the bat that GIB, it's not empty. So there's internal mesh, as you saw before. And for the pressure field for this simulation, they look very similar. For the velocity field, they look very similar. The mesh structure itself is also similar discretization. And you may not be able to see it, but there's some tiny red dots right here. And these are the different probe locations. And if we took the difference between the velocity at these two probe locations for these two different cases, we'd see that we're on the level of machine accuracy. And then finally, if we look at the history of convergence for the residuals, we'll see that both the GIB and the body fitted are both over top of each other. So it's extremely close. It's down to the level of machine accuracy. All right, so that was a static case. Let me talk a little bit more about moving mesh. And some of the most notable differences between a body-fitted moving mesh case versus a GIB, and you may not be able to see this with the resolution of your screen, but if you look on the right, you can see that the cells are moving, the cell shapes are moving, there's some deformation. If we move this a little closer, you'd see the aspect ratio of these cells change. So you take these nice orthogonal cells that are just nice squares, and now we're changing their shape. Numerically, it's fine. We're able to handle that with this body-fitted approach. But GIB, we don't have to change the shape of these cells far away. We are snapping at the surfaces, but we're not changing the shape in large groups of these cells far away from the surface. So that's an oscillating cylinder. Let's see if we can compare the forces between the two. So here we're looking at the X direction forces. We've got the neon green line, which is the body fitted, and we've got GIB. We see that there's a slight difference. There's a little bit of noise from the GIB compared to the body fitted. If we look at the mass loss between the inlet and outlet, it's on the level of machine precision, so 1 e to the minus 8. So for GIB, it's mass conservative. If we were to apply refinements, so here you can see the GIB surface inside this level 1 refinement right here, we've already reduced our noise of this GIB. And if we go a little bit further, we can see that it reduces even further, and we see very good agreement between these two approaches right here. Now, if we look at cylinder impact for a body-fitted approach, now we're squishing these cells as this cylinder approaches. The aspect ratio increases tremendously. If we go far enough, the cell volume might go close to 0 or near 0 or 0. And that will immediately cause divergence. For GIB, we're able to easily handle these types of approaches or these types of impacts at the wall. Let's look at unconventional motion. Here we've got a shape change. So this is a GIB with shape change. And then here we've got a GIB surface that's going in and out of the domain very freely without any issues colliding with the boundaries themselves. All right, so I've given a little bit about the methodology, talked about a motivation, talked about some moving mesh qualities. Let me talk a little bit about how this ties into Helix GUI. And typically in the webinars, I spend a lot of time diving into Helix GUI and how we set up these problems. But for today, because we're only doing 30 minutes, I'll really talk very briefly. So Helix GUI, it is a tool that we're able to perform our entire CFD analysis from geometry import to generating results. So we import the geometry, we can manipulate the surfaces, we can set up our meshes, we can set up our simulations, we can execute and simulate, we can perform post-processing to generate these results. Some of the key strengths are that it's a single cross-platform simulation environment. Windows, Linux, we can work on HPC. If you have cloud resources, we can work on that as well. It has advanced meshing and physics. One important characteristic is that you can scale up core count without a license. So running 10 jobs is the same as running, 10 cores is the same as running 100 cores or 500 cores or 1,000 cores. You can scale up to unlimited simultaneous jobs. So while one job is running on HPC, I can submit another job to run simultaneously. And then finally, one other core strength that I like is the Python macro for automation. So we can take this entire process of analysis to generate a result, and we can record a journal from within the GUI, and then we can replay that, we can automate that, we can, if we like to use Python scripting, we can definitely automate a lot of our steps. In terms of Helix GUI and the workflow and how this ties into GIB, Helix GUI is set up in terms of tabs. So we've got a meshing tab, a setup tab, a solver tab, and then we've got a view tab. And view tab is for post-processing. Within each tab, we have object workflow. So we start at the top of this object browser or tree, and we visit each one of these different objects and set things like mesh parameters, number of layers, or in this case, if we're in the setup tab and we're in solution, we're setting things like starting to set up physics. So we're doing a coupled solver, steady state, it's compressible. We could also set up multi-phase, we can set up adjoint here, and then we would go down through and set up different model parameters. So where does GIB fall into this right here? Actually, in the setup tab, there's a new application that we've put inside of the ribbon interface, and this is for creating or deleting internal boundaries. And so when a user clicks on the create, then you're given this dialog of being able to create a GIB from an STL surface, so a triangulated surface. And this is also assuming that you already have a mesh that's created. So we can create a GIB from an STL, or if you've created a face zone within the meshing process, then you can create a GIB from that down the road. What happens once we click run and we create this GIB? Well, what happens is now the object browser, the tree, has these new entries for what are internal boundaries. So this is different than what you might see in Helix 321. Now, once these are populated and we click on one of these GIB internal boundaries, then we're given this interface that looks very similar to what we're already familiar with in terms of setting up walls. So we can set up our stationary wall, our moving wall. We can set up a wall velocity if we like. We can control some of the wall functions for our turbulent setup. So if we have wall roughness, something like that, we can set it up. And then also if we're in a transient state, so even though we're doing segregated steady, if we did coupled or segregated transient, then we would have this additional tab right here on these internal boundaries to allow us to set up these motion functions. And these motion functions will let us do linear motion or rotating motion. So different types of physics we can start to approximate. All right, let me talk a little bit more about some of the applications. The first one that I'll talk about is a comparison between the static motion. So we've got different valve positions, and we're looking at flow rate versus valve position for different steady state simulations, versus looking at a fully dynamic behavior of this valve closing over time. And so this black line, this is what we use GIB to approximate. And in this case, we can see that there's a definite difference between looking at multiple static states versus this continuous dynamic state that we're looking at here. So if that's something that's important to capture during the design process, then GIB would be very effective in capturing this. Here's another animation just showing this valve motion. So here we've got a valve moving up and down inside of an internal combustion engine. And here we have a much better look at how these surfaces snap to the background. Okay, so this just kind of shows the dynamic mechanism of how this GIB surface is moving within the system. Here's another one with very similar behavior of this valve opening and closing, and we can see this dynamic behavior of the mass flow at each one of these outlets. So here we've got flow coming in, and then we've got these 4 outlets right here. Another application is looking at 3D tire modeling. So in this case, we wanted to see the tire rotating, and we also wanted to try to capture some of the velocity profiles of the fluid captured in between these tire grooves. Now, I wouldn't necessarily use this on a full automotive simulation where we're running hundreds of millions of cells and then try to capture the velocity in the tire grooves on the contact patch. But it's something that, at least this application, we wanted to investigate to try to approximate or calculate these velocity profiles within these tire grooves. Another one, we can see it's very slow, but we can see this is a multi-phase application, and this is a VOF solver, and we've slowly opened up this gate on a dam because maybe we'd like to monitor the forces on the surface of the dam, or we want to see what kind of velocity profiles happen near this gate or on the surface of this VOF or of the multi-phase surface. So we're able to get lots of information about the dynamic behavior of this particular application. While we're on the subject of multi-phase, here's just 2 more multi-phase applications. One, the GIB is being used as an inlet, and here we're injecting another fluid inside of the system. So there's lots of different applications for this that might inspire people to use GIB for that. Here we also have a 6-stop. This is very simple compared to the lifeboat application that I showed earlier. Next, we have something that is one of the cooler applications, and this was in Formula One fuel sloshing problem, in which we've got 2 tanks, and there's communication between these 2 tanks, in which there's a red door and a green door. And the red door opens from right to left, and the green door opens from left to right. There's also 2 atmospheric boundary conditions. So here at these kind of purple patches or blue patches up here at the top. And the initial state is that the left tank is full. This uses a multi-phase solver, so VOF, and the mesh was generated inside of Helix. The turbulence model that was used was K omega SST. And what we did was there's an additional acceleration force during cornering that would cause a shifting of the fluid inside of this domain, and there's some baffles to try to kind of reduce the forces of the fluid slamming against the wall. This is a simplified case compared to the real case, and what we're given is this gravitational force or gravitational vector versus time to simulate the cornering. And overall, see if I can get So we've got the fluid moving from the left to the right as we're cornering, and then we'll change directions. And then now the fluid will only go out this lower door right here and not come out here. Here, the pressure's pushed on this door to push it open at the same time. But we're able to have these kind of check valves or trap doors to only allow flow to go in a certain direction. This particular case took about 3.5 hours on one AMD EPYC 7351. And this was run on 32 processors. All right. And then finally, we have a polyurethane foaming process. And here the GIB was this injection. The GIB was this mold right here at the top. So the door of this mold. And so we can see the polyurethane foam expanding and the GIB interacting with it as it pushes up. And this was a custom application. All right, so let me leave you with a few take-home messages. First of all, GIB is generalized and will work with any solver and any boundary condition. So that's the goal. It's compatible with almost all field operations, and there's minimal performance impact. It strives to be robust and accurate. And right now in the GUI, GIB is situated, its uses right now are for walls. So dynamic motion of walls. Down the road, we'll extend it to different boundary conditions. And this is all dictated by how our customers would like to extend to particular applications. So there's potential for large deformations of structures, so beating hearts, sails, many fluid problems, for example, log jams, discontinuity capturing for multi-phase or shock capturing, phase change. So this has already been used to a certain degree on some custom applications. And then also some additional additive manufacturing and 3D printing. In terms of next steps, if you like, I'd say reach out to ENGYS and let's book a discovery meeting. Let's talk about functionality and talk about your application and where you might think Helix and GIB could fit into this. So if you have another software that you're looking to expand with other software or replace, we can definitely talk about that. A lot of times we'll do consultancy projects to do sort of proof of functionality. If that's not something you're interested in, I can invite you to visiting our blog where I talk about different adjoint topics, our work in AI and CFD, talk about our different products with Elements and Helix. And also, if you're interested, there's another webinar that is part of a series, and this is coming up on September 15th. And this one is about accurate wheel modeling with generalized moving reference frames, so GRF. And with that, I'll take a few questions.